Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 3, Lesson 5 on the side-angle-side theorem. Now in our last lesson we looked at the side-side-side theorem, which allowed us to conclude that two triangles are congruent as long as the three sides of one triangle are the same length as the three sides of another triangle. In today's lesson, we're going to see another way that we can prove that two triangles are congruent with a limited amount of information. Let's get right into it. All right, the side-angle-side theorem. As we saw in our last lesson on the side-side-side theorem, sometimes we can know only a limited amount of information about two triangles and still conclude that they're congruent. Our next theorem that proves triangles are congruent is the side-angle-side theorem. So let me bring that up to the top and then let's talk about what the side-angle-side theorem says. If two sides and the angle between them, which is called the included angle, in one triangle are congruent to two sides and the angle between them in another triangle, then the two triangles are congruent. All right, so we're going to get into the side-angle-side theorem and use it a bunch, but before we do use it, we need to prove it. And like all of these theorems, we're going to prove it by using rigid motions. So let's start off in exercise 1 and kind of set ourselves up for how we're going to do this rigid motion proof. Exercise number 1. In order to prove side-angle-side theorem, we need to first review an important idea about reflecting angles. In the diagram showed, angle GEF is congruent to angle HEF, letter A. If angle GEF was reflected across ray EF, where must the image of G lie? Justify. All right, I'd like you to pause the video now and think about this. If I take the angle GEF and I just reflect it across ray EF, where must point G lie and why? Pause the video now and go ahead and see if you can answer this question. All right, well here's the key. Point G must lie somewhere on ray EH, and we'll explain that in just a moment. All right, so somewhere on ray EH. All right, now why is that? Okay, let's talk about this a little bit. Now think about this. If we reflect this entire angle across ray EF, point E and point F will remain where they are because they're on the line of reflection. Okay? Now, reflections preserve angle measurements or angle measures. Right? Now think about this, right? We've reflected this angle, all right? If you will, E prime and F prime land right on top of E and F. G prime, though, would have to lie somewhere on EH in order to preserve that angle, right? So, therefore, G must map onto EH to preserve the angle. Now, if you said, oh, it's got to land on point H, well, let's take a look at letter B. If angle GEF was reflected across ray EF, under what conditions would the image of G fall onto point H? All right, pause the video now and see if you can now explain, all right, what would it take for G to land on H? Pause the video and go ahead and do that. Well now there'd have to be two things true. One thing that would be true, right, would be that angle GEF must be congruent to angle HEF, all right? But from letter A, we know that all that does is simply get G to land somewhere on EH, right? But that could mean that it might land here, it might land here, right? We don't know where G prime is going to end up being, right? All we know is that it's got to land somewhere on EH in order to preserve the angle measurement. But the other thing that would have to be true, right, is that EG would have to be congruent to EH, all right? Because distances are also preserved. Preserved under reflections. Right? And you can really picture this, right? I flip this angle over and G has to land somewhere on here because these two angles are congruent, right? But we don't know where G falls on here. But if G is the same distance from E that H is, then G prime would be where H is simply because the distances would get preserved. All right, really critical. And we saw that come up on a homework a bunch of lessons ago, okay? But I wanted to review it. Now we are ready to prove the side angle side theorem. Let's take a look at exercise number 2. We are now ready to prove the side angle side theorem. Just like with the side theorem, we can place any two triangles that satisfy the side angle side condition into a configuration like the one shown below using rigid motions. Explain why a reflection of triangle ADC across AC must map it on to triangle ABC. All right, so again, just understand, right? What we've got here is we've got two triangles that satisfy the side angle side condition, right? This side is congruent to this side, this angle is congruent to this angle, and then I made this side, this shared side, you know, kind of like put together, coincide with one another, because again, just like with our side theorem, if it wasn't already like this, we could just use rigid motions and map triangle ADC so that those two congruent sides matched up with each other. All right, now, why is it that when we take this particular triangle, and let's actually do it, let's just take that triangle and let's flip it across AC, right? It lands right on triangle ABC. Why must that be the case? Pause the video now and see if you can give an explanation for this. All right, well, as always, whenever we use a rigid motion or any transformation to map one figure onto another, we have to talk about where all three of the vertices go. I know this is probably getting kind of old, but let's get there, right? So first, A and C map to themselves because they lie on the line of reflection. So you're probably pretty sick of that particular line of reasoning, but it is true. So points A and C map to themselves because they lie on the line of reflection, right? And that only now leaves us with why point D must map to point B under this situation, right, under these conditions, and that's really right back to exercise number 1, right? D ends up mapping to B for two reasons, right, and they both have to exist. One being the angle DAC is congruent to angle BAC, right? That means that when we reflect, D will lie somewhere along ray AB. And because AD is congruent to AB, not only will D lie somewhere along ray AB, it has to actually lie at point B. All right? So, point D maps to point B because angle DAC is congruent to angle BAC and AD is congruent to AB. All right? And again, this whole idea, right, that one triangle will map onto the other using a rigid motion like a reflection then proves that the two triangles have to be congruent. So in any case where two triangles fit this side angle side scenario, one side congruent to one side congruent to one side, and then the angles between each of those congruent sides are congruent to each other, then we could always put those two triangles using some kind of mapping into this configuration. Then we could reflect one of them across that shared side, and it would always, always, always fall on the other one. It would be mapped to the other one. Now, we've got our side angle side theorem. We can use it. So now that we've proven a rigid motion, using a rigid motion, why the side angle side theorem works, we can use it to prove true triangles are congruent. So let's take a look at a proof of why two triangles are congruent. Exercise number 3. Do the following proof. Given L is the midpoint of segment HI and segment JK, prove triangle HLJ is congruent to triangle ILK. All right, now sometimes diagrams and proofs are going to get more complicated than this, but let's just be very clear. We're trying to prove that the triangle HLJ, it looked like HIJ from where I'm looking. HLJ is congruent to ILK. Let's see what we know so far. We know L is the midpoint of segment HI. What does that tell us? Well, that's going to tell us that HL and IL are congruent to each other. Okay? But we also know that L is the midpoint of segment JK. What's that going to tell us? That's going to tell us that KL is congruent to JL. But that's all the information I've been given, right? So yeah, sure, I have a side congruent to a side and another side congruent to a side, but somehow the angle in between those pairs of sides have to be congruent as well. Well, we know that angle HLJ must be congruent to angle ILK because those are a vertical angle pair, and we know that they're congruent. And that's it, right? We now have a side congruent to a side congruent to a side, and the included angle, or the angle in between the pairs of congruent sides, are also congruent. So let's lay out our proof. And as always, we start by our givens, right? So I first write down L is the midpoint of HI and JK, and then as a reason I say, well, it's given to me, right? That was told to me. Great. So what do I do from there? Well, I make that first conclusion. HL is congruent to IL, right? HL is congruent to IL. What reason do I give for that? A midpoint divides a segment into two congruent segments. And by the way, notice how I've kind of abbreviated things, like I've abbreviated midpoint, I've used the congruent symbol for the word congruent here. I could have even put in SEGS for segments, okay? That's all okay. You just have to communicate what you're thinking. Now, of course, I knew HL and IL were congruent because L was the midpoint of HI, right? But I also know that KL is congruent to JL for exactly the same reason. And I'd like to pause just for a moment here, right? Any time that you've got the same reason for two different statements, it is completely okay to combine those two. So if you wanted to say in line 2, HL is congruent to IL, comma, KL is congruent to JL, and then as the reason a midpoint divides a segment into two congruent segments, you should definitely do that. There is nothing wrong with that. I just really kind of want to spell it out for you here in separate lines. But if you want to save yourself some writing, put in HL is congruent to IL, KL is congruent to JL, right in the same line. A midpoint divides a segment into two congruent segments. My last piece is just those vertical angles, right? So in step 4, I'm going to say angle HLJ is congruent to angle ILK. And what will I say? Vertical angles are congruent, right? Simple enough. Vertical angles are congruent. So I have a side congruent to a side congruent to a side, and an angle congruent to an angle that lies in between those pairs of sides. So I can now conclude that triangle HLJ is congruent to triangle ILK, and I simply write down the SAS congruence theorem. Again, many teachers will be more than happy if you just write down SAS here, all right, as opposed to the SAS congruence theorem. But again, I want to try to be as proper as possible. I'd like you to pause the video now and take any time you need to write down any of the steps of this proof that you may not have had time to do while I was explaining it. All right, awesome. Nice kind of simple proof for us to begin. Let's see where we go from here. Another proof. Not surprising, we're doing a lot of proof in Unit 3. The bulk of our work, in fact, is going to be proof. Let's take a look at another one. Exercise number 4. Do the proof below, create your own t-table. Of course, I've got a t-table kind of written there. But let's take a look at our givens. Given, segment QR is congruent to segment SR. Segment RT bisects angle QRS. Prove triangle QRT is congruent to triangle SRT. All right, well, you may want to take a moment, pause the video now, and give yourself a t-table to work with. All right, what I like to do almost immediately, if possible, is I like to do something called marking up my givens. Okay, so I know that QR is congruent to SR. Let me mark that. QR is congruent to SR. All right, no problem there. Now I'm going to know that RT bisects angle QRS. That means that this angle and this angle are equal. All right, so I've got a side congruent to a side and an angle congruent to an angle. Where's my other side pair going to come from? It's going to come from the fact that they share side RT. So clearly, right, that side is congruent to itself. And that's all we'll need, right? A side congruent to a side congruent to a side, it just happens to be a shared side, and then an angle in between those pairs of congruent sides. Let's do our proof, right? Guess what? Statement 1, QR is congruent to SR, not surprisingly, given. Let's get that second given down. RT bisects angle QRS, also given. Now, just like before, if you really wanted to, you could lump both of these in the same line, and as their reason, you could just say given. All right. Now, right, we start to make inferences from those givens. So like right away, let's get something down here. Let's say angle QRT, right, angle QRT up here is congruent to angle SRT, and that is, of course, because a bisector divides an angle into two congruent angles. And again, you could easily put some things in here, like you could put a little angle symbol in for the word angle, the congruent symbol in for the word congruent. All of that is okay. Now, our final piece, right, was this shared side. And even though it seems probably pretty silly that you have to do so, we're going to write down that RT is congruent to RT, right? RT is congruent to itself, and anytime that you say something is either congruent to itself or equal to itself, your reason is going to be what we call the reflexive property. That should be easy to remember, right? Reflection in a mirror, right? You're seeing you're seeing the same thing there as hopefully what's on the other side of it. So finally, we have it, right? A side equal to a side, an angle equal to an angle, a side equal to a side. So we've got triangle QRT congruent to triangle SRT, the reason being the side angle side congruence theorem. All right, just like before, what I'd like you to do is take a moment, pause the video, and write down anything that you may have missed or because I was going too quickly. All right, great. So let's now take a look at exercise number 5. Given what you proved in exercise number 4, why can you now conclude that QT is congruent to ST? All right, now keep in mind, once we've proved something, that means we know it's true. All right, so what did we ultimately prove in this particular proof? Well, I don't need to circle the reason. We proved that triangle QRT is congruent to triangle SRT. Why, if we know that, can we now say that QT, maybe I'll mark this with 3 dashes and this with 3 dashes, is congruent to ST? Pause the video now and see if you can write something down. All right. Well, there's a variety of things that you could write down. You could write something simple down as just saying CP/CTC. Corresponding parts of congruent triangles are congruent. You could also say, since the two triangles are congruent and these are corresponding sides, they must also be congruent, right? All of that is fair game. The most general way of concluding that two corresponding parts of congruent triangles are congruent is just by saying CP/CTC. So, if this were a further part of the proof, we would finish it by saying QT is congruent to ST, and then the reason would be CP/CTC, right? Corresponding, never hurts to write this out again, corresponding parts of congruent triangles are congruent. All right, simple enough. Now, CP/CTC reasoning is really important, right? So let's talk about that. When you have proved that two triangles are congruent, you can then use CP/CTC, corresponding parts of congruent triangles are congruent, to conclude that corresponding parts of the two triangles are congruent, right? And again, it's really kind of cool. Understand, this is actually the thrust of most important geometry proof, which is that you have a limited number of conditions. You use those to prove that two triangles are congruent, and then you use that fact to go on to prove that two parts of those triangles are congruent. So let's take a look at exercise number 6. Do the following proof by first showing that triangle EHF is congruent to triangle GHF, and then use CP/CTC reasoning. All right, so let's again take a look at the givens. The first given, H lies on EG. Now again, telling us that H lies on EG really is just telling us that E, H, and G are collinear points, and that is kind of important. FH is the perpendicular bisector of EG. The perpendicular bisector of EG, so that is a whopper of a given. It tells us actually quite a bit. Now there's not much I can do to mark up the given H lies on EG. There isn't much there. But let's mark up what we've learned from FH is the perpendicular bisector of EG. Well, one thing that we learn is just the bisector part, right? And that tells us that EH and HG are congruent to each other. All right, just the fact that it's the bisector of EG. But the fact that it's perpendicular to EG tells me that this is a right angle and this is a right angle. Now, I want to be able to prove that triangle EHF is congruent to triangle GHF, right? EHF is this right triangle on the left, GHF is the one on the right, all right? So just like in the last example, the final side that we're going to use is right here. It's that shared side, HF or FH, depending on how you want to look at it. So we can use side angle side here. Now it's going to get a little bit involved, and I'll show you why. But once we've proved those two triangles are congruent using SAS, we can then just claim that EF is congruent to GF by CP/CTC, and that angle E and angle G are congruent by CP/CTC. All right, so let's do it. Let's get some of those givens out there. H lies on EG, given, right? FH is the perpendicular bisector of EG. Notice I've replaced the word perpendicular with the perpendicular symbol there just to save myself a little bit of writing. Awesome, given. Now let's get in some of that information that the perpendicular bisector tells us. So remember, the first thing I said was that EH is congruent to GH. Awesome. Well, why is that? A bisector divides a segment into two congruent segments, right? A bisector divides a segment into two congruent segments. All right? Now, what else did the perpendicular bisector piece tell us? Well, it told us, okay, sorry, this isn't the perpendicular bisector piece, this is that shared side. FH is congruent to FH, right? That's our reflexive property. Now let's get into what the second part of the perpendicular bisector told us, right? Number 5, angle FHE and FHG are right angles, right? That's very important. right? The fact that it's perpendicular to EG tells us that that's a right angle and that's a right angle. And the reason that we would give is perpendicular bisectors form right angles. Or you could say perpendicular lines form right angles, or perpendicular segments form right angles. All of those would be absolutely fine. Now remember, for side angle side, we have to claim a side is congruent to a side is congruent to a side, and the angles in between them are also congruent. We haven't done that yet, all right? So that becomes line number 6. Let me move this up a bit so you can see it a bit better. Angle FHE is congruent to angle FHG, and of course the reason is rather obvious, which is all right angles are congruent, right? By the way, all 60-degree angles are congruent, all 20-degree angles are congruent, all 54-degree angles are congruent, and all right angles are congruent, because by definition, two angles are congruent if they have the same measure. Finally, we can now say that triangle FHE is congruent to triangle FHG by the side angle side congruence theorem. All right. And now that we know that that right triangle on the left is congruent to that right triangle on the right, we can now conclude that EF is congruent to GF and that angle E is congruent to angle G. And because they have the same reason, which is CPCTC, I'm going to lump those two together right here. Angle E is congruent to angle G, and EF is congruent to GF, my reason being CPCTC. Corresponding parts of congruent triangles are congruent. All right, as always, I'd like you to pause the video now and write down anything about that proof that you need to. All right, final little piece, right? A proof like this seems kind of stock and normal and whatever, but we actually proved a very important thing specifically in this line. Not so much about the angle E being congruent to the angle G, but the EF congruent to GF. That's actually pretty important. And let's talk about that in exercise number 7. What important property of points that lie on a perpendicular bisector of a segment, such as F, is proven in exercise number 6? So keep in mind, right, all we knew was that FH, really, all we really knew was that FH was the perpendicular bisector of segment EG. And by knowing that, we somehow proved, right, and let me actually go in a different color here just so that you can really understand what we proved, right? What we proved is that EF and GF were the same length. All right, by just knowing that FH, isn't this a beautiful picture, that FH is the perpendicular bisector of EG, that allowed us to prove that EF and GF were the same length. So what important thing is that telling us? Pause the video now and see if you can answer it. Well, F is a point that lies on the perpendicular bisector, and it's the same distance from E as it is from G. So what we just proved were that points on the perpendicular bisector of a segment lie equidistant from its endpoints. Isn't that cool? Right? And that is a really important property of flat two-dimensional space. If I have a line segment, right, and I draw the perpendicular bisector of that line segment, any point that lies on it must be equidistant from one endpoint as it is from the other endpoint, the same distance away. All right, let's wrap this up. So we now have two ways of using limited information to prove that one triangle is identical to another triangle. The side-side-side theorem, which we saw in our last lesson, and the side-angle-side theorem, which we saw in this one. The side-angle-side theorem saying if I've got two pairs of congruent sides between two triangles, and the angle between those pairs of congruent sides is also known to be congruent, then we can conclude that those two triangles are congruent. All right, we're going to see a few other methods for proving triangles are congruent in upcoming lessons. For now, I just want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.